Okay, so let's start. The first thing that we're going to do is position representation. Position representation or position space, position space representation. What does that mean? We will use the eigenvectors of the position operator to represent the Hilbert space. So, in the position representation, in the position representation, the basis of the Hilbert space consists of an infinite set of vectors. The basis of the Hilbert space of the Hilbert space the basis of the Hilbert space formed by an infinite set of vectors that is R which are eigenvectors formed by an infinite set of vectors. The basis of the Hilbert space formed by an basis of the Hilbert space is formed by an infinite set of vectors which are eigenvectors of position operator R vector. Eigenvectors of position operator R vector cap. Full stop. Full stop. Therefore, I can definitely mention that R vector operator operates on your this R and provides you, it's just the eigenvector, provides you R vector into R vector kit. R vector into R vector kit. Done. So if this thing is clear, then we can go to the next one. If this part, up to this part, if it's clear, so we can go to the next part. So our vector represents the state of a particle which is at the position vector r corresponding to the eigenvalue this. So this is the eigenvector of the position operator with eigenvalue this. Now if this part is clear, so there are two conditions. One is orthonormality condition for a basis and there is the completeness condition for a basis. So the orthonormality condition can be stated as orthonormality condition the basis of the Hilbert is found by an infinite set of vectors which are eigenvectors of the position are found by the eigenvectors of the position operator. Okay, orthonormality condition, what is it? So orthonormality condition means all the vectors are mutually orthogonal and they are normalized to unity. So that can be written as R dashed, that is actually equals to del of R dashed minus R equals to del of R minus R dashed. You can write anyway. R dashed is equals to this thing, del of R dash minus R, del of R minus R dash. That can also be written as del of X minus X dashed, del of Y minus Y dashed, del of Z minus Z dashed. That's all. And apart from this, we have another condition which we call the completeness condition or closure property. Completeness condition, PLETE, completeness condition, which is the closure property as well. We can write it like integration dq bar r vector, or just simply r vector into dq bar is basically your identity operator IK. This has to be in all space. This has to be in all space. When I'm saying dq bar, that means dv, okay? That's a very important thing. dq bar is basically means dv, the elementary volume. That's an important point. Most of the people miss this point, but just don't. You people shouldn't do that. So that's one thing. And of course, the integration has to be done by all over the space. So that's another point for in the completeness condition. And once the completeness condition is done, you can just write it down. So it's an all space integration. Now, apart from this, so any function psi, therefore, the eigenvectors of position operator for a continuous basis of the Hilbert space. Of the Hilbert space. Full stop. Now, any arbitrary vector psi can be represented in this basis as any arbitrary vector psi can be represented in this basis as, okay, this has to be done over all expression. So you can just write it down as psi is equals to you can write down simply it's I cap into psi. Simply you can just write it down as in terms of I cap into psi because that's what it means. You can just simply write it down I cap into psi. Any vector, just because we know that that vector into dqr is equals to 1. So by using the completeness condition, you can simply write it down like this way. So I cap psi can be written as I cap into psi. Here I cap can be written as integration all space r dqr, integration all space r r dq bar. This entire thing into psi, which should undoubtedly mean that r vector here you must get r into psi and then dq bar. Just tell me one thing very clearly. This is a scalar quantity because it's a inner product. Inner product is always a scalar. So this is a scalar, this is a vector, this is a scalar again. Now, this thing can be written as, this thing I can write it as your, what can I say, psi of r vector. Psi r of r vector. That's the scalar. Then this r vector thing, get r, then dq bar. Then dq bar. I can write it like this. So this is my Cn psi summation over n. It's kind of like that thing. The psi vector can be written as like this way, where I might mention this is the wave function in the position space. That is called wave function of the position space corresponding to this ket. That's very important stuff. That's what we call wave function in the position space. So let me mention psi of r. is basically R vector inner product with psi is a complex scalar. That is projection of ket psi along the direction of R. Ket psi along R vector. That is also known as wave function of a particle in position space. In position space. That represents the wave function of particle in position space. That is nothing but the component of psi in the R basis. Component of psi in this basis. Okay. So psi of R can also be studied as wave function for the state vector psi. Therefore, psi R of R is basically R vector inner product psi is wave function for the state vector position space wave function. Position space wave function for the state vector psi. Now, according to Bond's probabilistic interpretation, according to Bond's probabilistic interpretation, Bond's probabilistic interpretation. What can you just write down? अगर हम लोग Bond's probabilistic interpretation को follow करें, then what can we say? According to Bond's probabilistic interpretation, the probability of finding a quantum particle in the volume dq bar, probability of finding a particle, probability of finding a particle exactly at point R. R is actually equals to probability of finding a particle in state psi, probability of finding a particle in state psi exactly at point R. At point R is R vector into psi mod square. Position vector corresponding to this eigenvalue, that is R vector into psi mod square divided by psi psi. If I take this as normalized, so this will be actually equals to psi R of R vector mod square. psi r of r vector mod square. Similarly, so that represents the probability of finding the particle exactly at point r. So what is the, just because we know that in a continuous basis a particle can never be at a particular eigenvector because that state is not normalizable. The state, if the particle is in state R, this cannot be normalizable. So this is unnormalized, so it's, the particle can never be in this state. So basically we can say similarly probability of finding the particle but we know in reality the particle in quantum mechanics can never be at a particular position, can never be at a particular position because if say say it has a particular position at time t, then the particle must be in the state suppose the particle has a particular position r at time t, r at time t, then the particle must be in a state r vector which is an eigenvector of the position operator, eigenvector of position operator, which is an eigenvector of the position operator with eigenvalue r vector, but the state r vector cannot be normalized. Therefore, the particle can't be in state R. If the wave function can't be normalized, so that means if the particle cannot be in that state. Okay. If the wave function cannot be normalized, so that doesn't represent a physically realizable state. So the particle can't be in state R. Can't be in state R. So it's more logical talk. So it's more logical to say about finding the particle between r2r plus dr. It's more logical to state probability of finding the particle between r2r plus dr probability of finding the particle between r to r plus dr. We can definitely talk about probability of finding the particle between r to r plus dr, because that is not at all risky, right? When we are talking about probability of finding the particle between r to r plus dr, that's another thing. It's not at all a risky statement. So let me just state it in this way. You can write it as like integration r vector psi, that is probability of finding the particle exactly at point r. When probability of finding the particle r to r plus dr क्या होगा? So in that range we can say that the probability doesn't change much. So we can just multiply it simply by dq bar. By dq bar divided by psi psi. And therefore probability of finding the particle between r equals to a to r equals to b is integration of this thing. And therefore probability of finding the particle between r equals to a to r equals to b, position vector r equals to b, is integration a to b ra to rb, integration ra to rb r vector into psi. Mod square dq bar divided by r divided by psi. Psi, of course, psi will be actually equals to 1. But yes, it will be like this. So I think we are done. Then we can just represent scalar product between the inner product between two state vectors psi and phi. And there is another important thing which we need to state, the inner product between two state vectors, that I can just represent here. The inner product between two state vectors or two kets psi and phi can be written in this way. Phi psi, which is your phi I cap psi, that is actually equals to I cap can be written as phi integration r vector dq bar into psi, and then this thing is easy. So phi into this r vector, r into psi is equal to psi of r, and phi into this r vector, phi star of r. So that thing will be actually equals to phi star of r vector psi of r vector, because our position specific function into dq r integration all space. This integration is all space actually, and I must mention that phi r vector is actually equals to r vector phi complex conjugate, that is phi r of r vector complex conjugate. That's all. And of course r psi equals to psi of r. R psi is equals to your psi of r. So from here it's very simple from this place. Okay, so I think this part was quite clear to all the students, that how did we mention the position space representation of a particle. If you have any question you can ask. On the next day we're going to be talking about the momentum space representation. Okay, thank you very much. And don't forget that जो भी बच्चे दिसंबर CSIR NET 2024 के लिए प्रिपरेशन कर रहे हैं, उनके लिए हमारे बूस्टर कोर्स लॉन्च हुए हैं, definitely which contains all the theory detailed lectures with PDF as a recorded format. Apart from that, in live classes we are solving enormous number of PYQs from various examinations like TI, JEST, GATE and CSIR NET. Apart from that, an enormous number of mock tests are available, which is very helpful for the preparation for examinations, reducing the chances of doing silly mistakes and the time management while giving the exams. And apart from that, PhD mentorship programs and PYQ books are also available. So all the students who are taking preparation for CSIR in December 2024 are advised to take the booster course as soon as possible, because more you delay, more you will be late for finishing the syllabus and then covering up it for the revision. Thank you very much. We will meet on the next session. If there is any question, you can always let us know in the comment section below. Thank you.